In this video, we will consider the following problem. A given is some integer, which is a sum of three terms. m1 and m2 are positive integers. We need to show that n cannot be a perfect square at any m1 and m2. First, let us recollect what is a perfect square. The number n is called perfect square if it can be represented as a square of other integer. The perfect square has a very interesting property, namely, the remainder after dividing the square of any integer by 4 can only be either 0 or 1. In mathematical notation, it looks like this: n squared modulo 4 equal 0 or 1. Let's solve this problem using this property. We suppose that n is the perfect square, so it can be represented as square of some integer. In this case, the remainder after dividing n by 4 can be only 0 or 1. Let's look carefully to this integer. The first term, 4 to m1, is a multiple of 4 because m1 is an integer. It means that remainder after dividing this term by 4 is 0. Similarly, here 12 is also multiple of 4. 12 is 3 times 4. So this term also has no remainder after division by 4. 3 to 3 is a 27, and 27 has remainder 3 after division over 4. So the integer n after division by 4 has a remainder equal 3. But this is in contradiction with the property which we considered above. It means that n cannot be the square of any integer, so cannot be a perfect square. Problem is solved. Now we step back and make a proof of the property which we used. We start the proof from the case when n is an even number. In this case, n is multiple of 2 and can be represented in this form where k is an integer. N squared is equal 4 times k squared and is multiple of 4. It means that the remainder n square mod 4 equal 0. And then we consider the case when n is an odd number. In this case, n equal 2k plus 1, where k is an integer, n squared given by this equation, and two terms are multiples of 4, so they provide no remainder after division by 4, and 1 is a remainder. So n squared mod 4 equal 1. There is no other options for integer. They are either even or odd. And we see that in that cases the remainder n squared mod 4 equal either 0 or 1. The property is proven. If you like this video, you may want to hit the like button, to leave a comment, and to subscribe to my channel. Thank you.